Oh
We
no.
all forgot this time.
Well, yeah, I have a record. I have to keep my record up. There's never ever ever remembering to record. Okay, thank you. I'll add that in at the beginning. Yeah. Okay. So let's go to amplifier 2. So what kind of amplifier is this?
Is it a current amplifier?
It could be, but in this class, since IB, you're right, there's an IB here, but for a couple reasons, actually 3 reasons, I'm treating this as a voltage in device. One is because I want to. Second one is that then I can treat MOSFETs and BJTs the same. And also that if you treat this as a voltage input amplifier, you get an exponential change in current. And so you get an exponential change in V out, since you're throwing that current across a resistor for, say, a common emitter. But if you use it as a current amplifier, IB gets multiplied by a constant. Whatever beta is, that's what IB gets multiplied by. So you don't get that exponential increase in current. But you can treat this as a current amplifier. And there's actually a separate model that instead of having instead of having this, I'll give you the alternate model, but we won't be using it this quarter. So the alternate model for a BJT is and it's the same thing. This corresponds to the base, that corresponds to the collector, that corresponds to the emitter. So that's the alternate model, and it's just fine to use that model to do small signal analysis too. But just because we're also doing MOSFETs, I'm using the GM version of the small signal model. What this model right here tells you that something that was told to you in 306 and possibly 307 was a lie. Does anybody see it? Draw in. What were you told IC equals?
IB times beta.
IB times beta. Is IC equal to IB times beta here?
No.
No. Why doesn't it equal IB times beta?
RO.
Yeah, there's some current coming through over here. And so kind of the base current is IB times beta, but then what's this RO represent again? If you had to give it a name. Okay. So this is that when you change VCE, there's a little bit change of current. So this branch right here represents how much the current changes when you change VCE. Okay, so this is an alternate model. I'll look for you to use the model that uses GM instead for this class. But you can do just the exact same math just using this model. Okay, so second question is, what is the R out? Again, since the transistor is, we're treating it, well, it's going to be a current out device. What's the R out at that node for a BJT?
Isn't it RO as well?
Yes. Okay. So first step, again, we're looking at perceived resistance. So if I change that voltage, how much does the current change? GM VBE RO, and the emitter's connected to ground. VN's here. Here's your I test, and the collector is your V test. And again, since you're trying to find R out, you get to use the 2-port rule. That grounds that. If you ground V in, then what's VBE?
Zero.
0. And then you get to get rid of this. And what you end up with is, I wish I had art skills here. There's your output, and so your R out just equals RO. Okay, then one more step. I'm trying to give you 20 minutes for this next thing, so we can actually work through it at the end. So we started out with a common emitter with a passive load. And we saw that when we made R bigger, then V out moves more. And when V out moves more, that increases the gain. So a bigger R means bigger gain. Okay, and then we got to a point, we made R bigger and bigger and bigger, and then it got to a point where we could hardly have any current going through there. If you made R really big, like a mega ohm, then even at a milliamp, at a single milliamp, now you've got 1,000 volts across that resistor, and that can't happen. So there's a limit to how big this R, how big you can make that R. So we replace that with an active load. And V bias. Okay, so my next question to you is, we're using this active load right here in place of the resistor. So I want to know how big a resistor that looks like. So instead of talking about the R out of a circuit or R out of an amplifier, I'm saying I'm using this in place of a resistor. So I'm using this in place of a resistor. I want to know, this is V bias. I want to know how big a resistor it looks like when I connect it to this node. This looks like a resistance. How big does that resistance look? So my question is, how do you use small signal analysis to solve for how big a resistor that looks like? I think that's a sentence. Not a very good one, but so is the question clear? So how about, that's my next challenge to you. See if you can figure out what that R is looking into that node. And the last 2 examples should help you out.
Tina, is the small signal analysis for PNP the same as NPN?
Yes, but it's flipped upside down. Now the emitter's on the top. So it's the exact same small signal model, but everything's upside down.
Okay.
Tina.
Mhm.
I'm curious, like, isn't the resistance like different for the PNP on top depending on the V bias that you're setting? Or is it always that same resistance, like, based on what we went over?
That's one thing that doing the small signal analysis will tell you. If VB shows up in your equation,
That's the
then
thing, though. In small signal analysis, we would ground that, so we can't, like, it'll never show up in the equation. So is that the right route to go? That's why I realized that. That's why I was wondering. So it doesn't matter what
So
that V bias is.
you're totally right. It doesn't change your small signal analysis. Let's do that. Let's do that real quick. So for PNP, remind me if I don't answer your question in a second. For the PNP, just take this whole thing. And, well, that didn't work very well. But you get the idea. Let's do flip it. See if this actually works. Flip it. Well, it's not beautiful, but yeah, so you just turn it upside down. Is that okay?
Yeah, that's I have that.
Okay. Okay. And then now this is the emitter since it's flipped over. That's the collector and this is the base. So as you mentioned, this is a DC voltage, and what do you do to DC voltages?
You ground them.
Ground them. So this is grounded. This is going to the supply. Whoops, where did it go? This is going, oh wait, no, yeah, this is going to the supply. And what do you do to DC sources?
Ground them.
Ground them. And then this right here, this is what you're curious about. You're trying to figure out how big a resistor it looks like at this node. So this is like you have a black box here, and then you'll have the resistor. You have the resistor in here. And now you only have access to this point. Now it's on the bottom, but it's the same problem as when we were doing it for the MPN. So this would be your V test, and this would be your I test. And then do you get rid of anything?
Yeah, you can get rid of that current source, the
Yeah.
GE, because it's grounded. You end up with, I get that you end up with RO, and then
Okay.
if you do the total analysis, you'll end up with RO of the PNP in parallel with the RO of the NPN.
But not
But
for
what
this
if-
one, since it's only a single transistor, but exactly, if it's an active load, that's what happens.
Oh
So-
yeah. I meant for both the PNP and the NPN, like the total RO would be the two ROs in parallel. But,
Uh-huh. But
is
so
that-
let me take this one more step.
Oh, okay. Sorry.
So this is the parameter for a single transistor. So we got there, this is the right answer. But let's take it one more step. If you actually wanted to find the value of this, you have to use those equations that you found using derivatives. So what's the equation for RO?
The early voltage over the collector current.
Yes. And what determines the collector current?
Oh, okay. I see. The VBE is like an exponential component of the collector current.
Yes. So you'll always get RO, but the current's going to be different depending on how you biased it.
Okay, but won't it always be forced to the current of the NPN on the bottom? So is that like, so then wouldn't technically one of the base voltages just be just being forced to be whatever the, like, you get what I'm trying to say?
Yes. So the top transistor, it kind of does whatever the bottom transistor. So on this, whatever this transistor, should use a red or something. Whatever this transistor conducts, this one also has to conduct. And as it tries to accommodate the current that the bottom transistor is telling it to conduct, that's why V out moves here.
Okay, I see. So then V bias play a role in how much that voltage is for at that node where V out is, like how much it changes?
Yeah.
Okay.
But when you find this value right here, that's only for the value at the biased. What you bias it for a particular current,
Okay.
and then it does go above and below, and your R out is actually changing a little bit. But
Okay. Now that makes sense. Thank you.
okay, yeah, we're kind of fudging. We say, okay, well, it's too hard to come up with an equation that tells you how the gain changes when the current changes, and you know that this transistor right here is changing the current. You say, okay, well, I'll be happy with just where it's biased, and then assume it just goes up and above and below that a little bit, so we're about at the same gain.
Okay, I see.
Yeah, all of this is for hand calculation, and again, the equation that your simulator uses is horribly complicated. So it's extremely difficult to hand calculate an accurate gain. This is to make it so it's human friendly.
Okay, got it. Thank you.
Okay. All right. So we've got this. So if I could just looking at this active load, what's a way to make this this R look bigger? Remember, it's this R. What it's saying is when it's big, this is the perceived resistance. So in other words, when you change the current through it, the voltage changes a lot if it's a big resistor. Okay. So how could I make this look, how could I increase gain? In other words, how could I make this look like a bigger resistor?
Could you try to keep the current, or the current through the lower transistor smaller?
Yeah, if you bias this top transistor not to conduct very much, then in theory it's acting like a bigger resistor. Okay,
Is
but
that decreasing V bias?
that would be increase. Since it's a PNP, it would be raising it.
Oh, okay.
But yeah, decreasing the VB exactly. So that can actually give you a steeper gain. But let's say, so we went from a resistor to a single transistor. I'm just going to start with the PNP version of this and see how it goes for you. But no, let's do it. Let's do the NPN. Let's do the MOSFET. MOSFET was the plan here. Here's a challenge for you. So today you saw we were working with single transistor amplifiers up to now and finding the RNs and ROuts and gains. And then I just threw a single transistor at you and said, okay, assume this is an amplifier now, what's the R out? So any circuit that comes at you, if somebody asks for the R out, it's the same process. You replace the transistors with the small signal models and then put a V test and an I test on it and see what resistance you get. So I'm going to give you a random circuit. It's not an amplifier. And assume that both of these make the transistors happy. In other words, this V in and this V bias, put them in the forward active region. And I want you to try to work through, this is slightly messy. It's less messy than Monday's problem and more messy than last week's problems. So what I'd like you to find is the resistance, the perceived resistance there, the small signal resistance at that node. Tell me if that looks like a big resistor or small resistor. Try to come up with the equation for that. Oh, I forgot to put you in groups. Do you want to stay here or do you want to do breakouts? Why don't you stay here so you can ask questions and everybody can hear the questions?
Tina, is the bias MOSFET supposed to be PMOS or NMOS?
NMOS. These are both NMOS. And this is a special name. It's called a cascoded. Cascoded, you can call it a composite or, yeah, let's just call it a cascoded transistor. Cascoded means you have two of the same kind stacked on top of each other. Let's see what cascoding does. Cascoding is actually a verb. Let's see what cascoding does to the R out. And use subscripts so you can keep track of what value belongs to which transistor.
Is M2's body grounded?
Both of their bodies are grounded.
Okay.
Let me go one step in just in case there's some people that are that don't know where to go with this. What's this tell you? If you're looking for R out, what's the nice thing you get to do? Zero the input. Okay. So I get to zero the input. And again, I like to keep track of things. So this is VGS1. This is VGS2. I'm just going to call this Vx to make it easier to talk about. And what's VGS1?
Zero volts.
Zero, yeah.
So what do you get to do?
Drop out the two bottom current sources.
Yes, that one goes away because of VGS being 0, and this one goes away because the source is 0 and the bulk 0, so that goes away. So I'm going to redraw. Okay, I'm going to do one more step just in case people are having trouble getting equations. So if I'm trying to find a value for R, say for R out, that's V test over I test. I like KCL, so I'm just going to take I test, even though I don't know where to go. Current seems to work better. So that's G. How's it going?
Could you change VGS2, both VGS2 and VBS2 to be negative Vx?
Yeah, so if you look at this equation, you only want voltages and currents that show up in your target equation. And, there we go. You only want voltages and currents that show up in your target equation. I test is in there, so you want to keep that, and V test is in there, but you have to get rid of that voltage, and that voltage from this equation. So just as you said, that's exactly where to go. So VGS2, what did you say it was?
Negative Vx.
Negative Vx. So VGS2 goes from this node to this node, goes from this node to this node. VGS2 is 0. This node is Vx, so 0 minus Vx gives you negative Vx. And then you already were ahead of this, but VBS2,
That's also negative Vx because the body's grounded.
Okay, negative Vx again. So now we've got rid of that one and that one. Now we have an equation with only Vx in it. So we also need to get rid of Vx. So anybody, there's a trick here to find Vx. Anybody see the trick?
Is it I test times R naught or R0?
Yes. Yeah, so this I test, it comes in here and it splits into 3 branches, but then it has to come back together to come down through the bottom. There's no new current introduced by these sources. It just splits I test between these 3 branches and then it comes back together again. So when it comes back together, it's I test again going through RO. So I pen stopped working. Okay, let's try the mouse. I test. Oh, this is too slow. There we go. I test times RO1, which means VGS2 is negative I test RO1. Sorry, this is not writing very pretty. And this is also negative Vx. So this is also I test RO1. I might go over by a minute. If you need to go, I'm recording, so you can check it out later, but I'll keep going here. So our now I have enough information to replace all these voltages in the first equation. You have I test equals, now this is negative I test RO, so you have GM2. Actually, VBS2 is the same thing, so I'll do GMB, sorry. I should be using GMB. 2 times I test times RO1, and there's a minus sign up in front here. So sorry about that. So that takes care of this term, and then we have plus V test over RO. Which RO is that? V test, that's RO2. And then minus Vx over RO, so that's I test times RO1 all over RO2. Yep, I'm going over. I think I need 1 more minute, and then I can get through this. I'm going to move all the I tests to one side. So I test plus, well, actually, no, I test times 1 plus GM2 plus GMB2. So I've just moved this term over to the other side, times RO1. And then is there any other I test? There's another I test. So that's plus RO1 over RO2. And that all equals V test over RO2. Up to there, okay? What we actually want to find is V test divided by I test. So if you divide both sides out, V test divided by I test, you get RO2 times this whole thing. Okay, which do you think is the biggest term in this inside the parentheses right here? Figure ROs are like 100K, and figure like GMB is from 0.1 to 0.01. Which of these 3 terms is going to be the biggest?
GM times RO.
Yes, so let's do an approximation here, and this is what you'll see in textbooks. You'll see And also GM2 is usually 10, 100 times bigger than GMB. So I'll write that out on the notes in a second. But RO1, RO2. So what was the resistance looking into the collector of a BJT? That was RO. And if RO equals about 100,000, now you have, if that was 100,000, now you have 10 to the 10th. Your resistor looks like 10 to the 10th. with just 2 VD sats across it. I'll go over this again at the beginning of the next lecture. But cascoding is a way to get a gigantic resistor, like a giga-ohm of resistance with hardly any effort and hardly any voltage across it. Once again, time management, sorry. Any questions? Okay.
Thanks, Prof.
Absolutely. So the reason why I use VBS instead of VSB is because that's how my textbook did it. I think the sign convention inside the VT equation, I should go back and look at that. Actually, I'm going to put that on my list of to-dos to try to figure out that sign. But yeah, that's just how I was taught and how my textbook. But when it's in the small signal model, that's the convention that my textbook used when I took this course.
So what direction should the current be flowing if you use, say, VSB?
VSB would go the opposite direction, so it would be going up.
Okay, that makes sense.
Yeah, but I'll clarify that just for my own brain too. I never get this right. Okay, go ahead and keep working. I'll introduce the question again for those who's out there. So the first part of this was whether this is an amplifier or not. And the answer is actually yes. And it has a voltage input and a current output. Just a single transistor is an amplifier on its own. And if you can't remember how to name this amplifier, find whatever the output is, which is current in this case. Find whatever the input is, that's voltage. And remember that gain is output over input. Again, the output's current here, input's voltage. So you have currents over volts, which is conductance. And so this amplifier as a whole is a transconductance amplifier. Okay, and then the question that I gave is, what is R out? And to find R out, you first have to find where the output is, and the output is at the drain. Okay, I think I have it recorded now. Okay, so what's the first step if somebody asks you for the perceived resistance or the small signal resistance?
Draw the small signal model.
Okay, so I'll do that. And in the VT equation, it's VSB, the one that I have on the slides, but generally in the small signal model, it's VBS, and I'm going to go back and try to figure out why that's flipped, but right off the top of my head, I don't have an answer for that. but I'm going to use VBS inside the small signal model. Okay. Do you want another minute or? Okay, so we've got our transistor. What's the next step you do?
You're meant to ground V in, but V in is just. Oh, actually, that does help a little bit.
So yeah, you notice you figure out what you're looking for, and that's R out, which is V out over I out. And then what do you get to do with when you're finding R out?
Ground V in.
V in equals 0. So this was V in, but since we're doing an R out, we get to ground it. And I mean, I could write I out here, but just to kind of get uniform names, I'm going to call that V test and I test. It's supposed to be I test. And then what do I do to the source?
It's grounded, right?
It's grounded, yes. So on the original circuit, source is grounded, so we get to ground that. My mouse has stopped, my pen stopped working again. Okay, alrighty. Now, before we go on, it's always good to see if you can clean things up.
You can remove the leftmost current source, dependent current source.
Okay, I always like to write in voltages that show up places. So here's the source bulk. That's VSB. I guess this should be plus minus if it's VBS. Okay, and why do you get to get rid of this current source?
Because V in is grounded and the voltage source at VS is grounded.
Yes, so gate's grounded, source is grounded, so VGS is 0. This goes away. Anything else you can do?
The other current source goes away too because VBS is.
Okay, yeah, the source is grounded and the bulk is grounded, so VBS is 0, so that goes away. And there isn't anything else you can simplify out. So what's left is you have RO ground and you have I test and V test. And you really don't have to do any math. What's R out?
RO.
RO. And you're done. So the R out of this, I forgot to say this in the last class, so it's good here, but this R out, is RO big or small? R sub 0, R sub O. If you remember, there's an equation to help you find the value of it in BJTs. Do you remember the equation for RO?
VA over IC.
VA over IC. This is a MOSFET, so it's a little bit different, but VA over IC, that's pretty darn big. VA could be 100, and then if you're at 1 milliamp, that's 100,000. So in this case, anybody remember the MOSFET RO equation?
Is that like 1 over like VDS lambda or something like that? I can't really remember.
Yes, lambda IDS. So again, if you have a milliamp, and then your lambda is 0.1 or something like that, now you have 10,000 or something like that. So this is a really big R. But wait a minute, didn't we want what for an ideal op amp? Do you like big R outs or small R outs?
Small.
small. But this is a big R out, but it's actually good to have a big R out. Do you know why?
So the current can be relatively constant?
Yes, exactly. Okay. When we had a common emitter, I said when we were looking at the loading factor, I said you can model that as a Thevenin equivalent. What kind of, is it voltage or current output for a common emitter?
Voltage.
Voltage, so you want to use a Thevenin equivalent, but what's the output of this circuit?
Current.
Current, so what would you use if you wanted to model this connecting to another circuit?
Norton.
Norton, and if you remember the Norton equivalent, the resistor is here, and this is what connects to your other circuit. So you want a big R, so all your current will go to the next circuit. So actually for a current source, it's great that R is big. For a current output device, for a current output device, it's great that R out's big. Okay, any questions on how we got to RO being the output for this transconductance amplifier? Okay, since we're there, let's do one more. This should be friendly now. Okay, is that an amplifier?
Yes.
What kind of amplifier?
Transconductant.
Yes. So this is also an I out. What's its R out? Or perceived resistance or small signal resistance?
RO.
RO. Okay. So if you went through the whole thing, darn this pen. If you went through this thing, that's R pi. I can't write with the mouse. My roommate for 1 quarter was so good at drawing with a mouse. I always thought that was, she drew all sorts of cartoon characters with the mouse. Never figured out how she could do that. Ah, it's back, okay. You have V in here, this is grounded. This is your I test. And your V test. And what happens? It's pretty much the same steps. So if it's R out, you get to 0 your V in. And again, I always like to write in my voltages. VB is 0, so this goes away, and this goes to RO with your V test and I test. And your R out equals RO. So same thing. Okay, ready for try number 3 here? Let's do, so we had kind of 2 levels of common emitter amplifiers. We had this one, and it's common emitter with passive load. And the way this thing works is your bottom transistor generates current, and you throw it across the resistor to convert the current to a voltage out. So this generates current, and the resistor turns that current into an output voltage. Okay. And the bigger R is, the more V out moves. And how much V out moves tells you how big the gain is. Okay. So the bigger the R, the better in theory if you want a big gain. But once you start to get like to a mega ohm or something like that, if you have 1 milliamp through your amplifier and a mega ohm resistor, that's 1,000 volts across that resistor, and you just can't build that circuit anymore. So there's a limit to how big, sorry, there was a fly, how big you can make that resistor. So we said, well, this is interesting. If I do this, wow, all of a sudden I get a bigger gain. So on this one, this right here is acting like a big resistor. That's how you get big gain. So my question to you now is, how big a resistor does that look like? And in this case, you're looking up this way and saying, oh, how big a resistor does it look looking up into that transistor? So how would you find that?
Would you just find the R out of
Yes. So how would you do that with small signal analysis?
draw the small signal model for a PNP?
Okay, I'll draw it for an NPN, and then we'll go to the PNP. Actually, I'm not going to draw. Let me get rid of this. Oops, I already did it, almost did it again. Okay, so that's the NPN model. How do you find the PNP model?
Flip it.
Flip it. So if you just take that, that's the NPN, just turn it upside down. Whoops. Kind of do it better than that. And so everything that was on the bottom for an NPN is now at the top. So it was an emitter at the bottom for an NPN, so now it's at the top. Collector was the top, so now it's at the bottom. And the VN was at the top, so now the VN is there. This is our pi for the PNP. This is your GM VBE. This is our RO. Okay, and then if you look at how this is connected up, the emitter is connected to the supply. So what's that do? What do you do to supplies?
Ground it.
Ground it. So that's grounded. And now, since it's a PNP, we're actually trying to find the resistance. So need to put current into it, I test and V test. What do you do to the V bias?
Ground.
Ground it. But let's see, this is the R out of that transistor. Aren't you supposed to zero V in? Where's V in on this thing?
Is it VC? Or is it not C?
It's a trick question, sorry.
No VN.
No V in. Okay, so the R out rule should actually read, if there's, sorry, I was being mean. If there's a V in, zero it. If there's no V in, then don't worry about it. Okay. So this is our kind of leaning circuit here, and this gets grounded. So what happens?
R pi goes goodbye.
Our pi goes goodbye. You've got a ground on this side, ground on that side. And then what else goes away?
Current source.
The what?
The independent current source or the
Okay.
dependent.
For some reason, I heard that as the Smurf goes away, so I was confused. But yeah, current source. Okay, and so this also, comes out to a resistor of size RO of whatever your PNP is, and that's why it acts like a big resistor. Okay, in the model, what does this branch represent? So each branch represents the change in IC for a different voltage. So what's the RO branch represent?
The change in IC relative to VA?
So For those, it's operating voltage. The VA's a characteristic of the transistor. So VA never changes, but what does change?
VCE.
Yeah, and what's that called? When VCE changes and the current changes, what's that effect?
Is it base width modulation?
Exactly. So RO represents base width modulation. So the only current change here is with respect to VCE, and that makes sense because you've biased this transistor, so this voltage isn't changing. So there's no change when VB is not changing, so there's no change through this branch. But VCE can change, so there is a change in current through that branch. So it makes sense that that this goes away, but this stays. Okay. In the other class, I know I'm running a little bit. I think I have 3 minutes compared to the other class. So let me mention one more thing. In this class, I'm using this model for BJTs. There's actually a second model. And this is just fine to use, just not in this class. I won't be using it, but any place you used the hybrid pi model, you can use this model just as well. This model right here actually tells you something that people have been telling you since 306. It suggests that that's all a lie. I'll give you a hint. You know John Oliver? The other day in meeting, we were all thinking about something, and he found the music for Jeopardy. Just started playing it. Thought that was funny.
Is it that beta IB is equal to IC?
That's what you've done in all your classes, right?
Yeah.
But is it in this picture?
No.
Yeah. What's the additional value that's being added on?
IB beta times R naught?
It's actually a separate current. So, but yeah, it's this current that everybody's been telling you equals IC. Plus, you also have some current going through RO. So the IC equals beta IB ignores base width modulation, but this model takes it into account. Okay, so now final question, and we'll go into it more in the next class. This is used a lot. There's a technique called cascoding, and cascoding means that you stack two of the same kind of transistors on top of each other. And this small signal analysis, it's messier than the ones it's not as messy as the ones we did on Monday, but wait, today's Wednesday, right? Yeah, okay. It's not as messy as the ones we did on Monday, but messier than the ones we did last week. So it's good practice. But this is called cascoding. It's also called cascoded transistors. That's the verb. And if you try to type it in Word, it always corrects it to cascaded. But this is actually cascoded. So my challenge to you is for this for cascoded transistors, you have some current coming through here. My challenge to you is to figure out the resistance you see at this node. So we've been doing single transistor amplifiers, like the common collector and the common emitter and the common source, and you found R in, R out, and gain for those amplifiers. This technique, the small signal analysis technique, can be used on other random circuits that people throw at you. So this is, we actually just did that with a single transistor. Like, you didn't really think of that as an amplifier. And I said, oh, well, what's the resistance, the perceived resistance at this terminal? And you were able to figure it out with small signal analysis. So this is the same kind of thing. See how big a resistor this looks like at this terminal up here. And if anybody's having trouble getting started, just wave a hand and I'll get people started.
Do we need to be using test currents for this? Test voltages and currents?
Just to be kind of consistent, when you do the small signal picture of this, it's nice to use V-test and I-test. It's just kind of a general convention that people use.
Professor, I just have a quick question.
Okay.
So to do this, we're going to be finding the R out for these two systems, these two transistors in the same system. Would that essentially be like we just do the analysis for one when they're stacked on top of each other?
For this one?
Yeah.
For this one, you want, my pen stopped working yet again. Treat that as a single circuit, just like you did for a common emitter. So this whole thing is your new circuit, just like you treated a common emitter with the resistor and the transistor as a single circuit. My ears hurt. Oh, and use subscripts so you know what value belongs to which transistor. We'll call this M1, M2. How are people doing? Having trouble getting started? Try to work through this and see what you can do with it.
Are we assuming that the bodies and sources are like connected?
Assume that they're all all the bulks are connected to ground.
Okay.
Yeah, sorry, I needed to say that. Okay, I'll interrupt you just for a second, just in case there's anybody having trouble getting started. So I saw 2 transistors, so I just threw down 2 small signal models. And then next step would be seeing how these are connected. And this is small signal, pen's gone again. This is for the bottom transistor. So if I look at the bottom transistor, this is actually connected to Vin. The source is connected to ground. And then what about the drain? Where's the drain connected?
The drain is connected to the source of M2.
Okay, perfect. And then what about the gate? What happens to the gate?
Grounded.
Grounded. V bias is a DC voltage, so that gets grounded. And then one thing that I see some people do is they're so used to doing common emitters and common sources that they try to draw V out down here. But V out has to go on the same terminal as it did on your original schematic, your original circuit drawing. So that would be right here. There we go. How's it going? Any questions? Okay.
Are we going to have to do KVL or KCL at some point in this analysis?
Yes. So this right here, this is just like with the single transistor amplifier, or the single transistor that we were looking at as an amplifier. This right here, that's considered your R out. That's the current going into here. That's actually the output of this cascaded amplifier. And so this is actually, we're looking for R out. So let's make that official here. We're looking for R out. And R out, you know, is V out over I out. Or sorry, V test over I test. Let's keep the names correct. Or names agreeing anyway. And then what nice thing do you get to do?
0 VN.
0. So let's do that. Okay. So then I forget what your question was.
Oh, my question was if we're going to use KCL at some point.
Yes, that's why I wrote the equation. Yeah. So again, I always like to. We're not there yet because you have to do the cleanup step. If there's anything you can get rid of, you want to get rid of it before you start doing KVL or KCL. So let's do that first, and then I'll speak to that. But I always look at this equation. I'm trying to find R out, and I know that's V test over I test. I look for a current in that equation, and I see I test in here. So I would immediately do KCL for I test. usually gives you the cleanest equations. Okay, so anything we can clean up here? Anything we can get rid of? And I'm going to name this Vx just to have this a name for this node.
You can get rid of both of the dependent current sources on M1.
Okay, exactly. So again, if you write in the voltages, this is VGS1, and gate 0, source is 0, so VGS is 0. So this goes away. And then if you do the voltages here, VBS, source is grounded, bulk is grounded, so VBS is 0. And this goes away. So I'd be lazy. So now I can get rid of and I don't need the bulk voltage anymore because I got rid of VBS. Oh, I guess I do, huh? Because it's used up top. My bad. But I don't need this gate voltage anymore. Already taken care of. Yeah, I don't think there's anything else I can simplify. Any questions how we got to this version? Okay, so next step is again, we're trying to find R out, which is V out over I out. And again, I just like KCL better, so I'm going to make an equation for I out. And, or I test, my bad. Ah, I keep doing this. Sorry, y'all. So this is the current going into the node. That has to equal the current coming out of that node. So I have GM2 VGS2 plus GMB2 VBS2 plus V test minus Vx over RO2. Okay, now the first kind of the mechanical way to go about this is to say, okay, I want an equation with only V test and I test in it. R out, the R out equation only has V test and I test in it. So any voltages or currents in this equation that I just came up with that aren't V test or I test, I have to get rid of them. So I test, that's good. But VGS, we have to get rid of this one. VBS, we have to get rid of that one. There's V test, that's in the R out equation, so we get to keep that. And then Vx we have to get rid of. So anybody figure out how to get rid of VGS2? How about, okay, how about this? Did anybody figure out how to?
Is that Vn minus Vx? Or, wait, never mind.
Could you write VGS in terms of Vx?
Exactly, so let's do that. My pen's gone again. I'm sorry, I keep saying that. Let's see. There we go, it's back. VGS2 equals, and what is it in terms of Vx?
Zero minus Vx?
0 minus Vx. So, okay. So now we have an equation for this. It's not in terms of V test and I test yet, but let's keep going just because I know the answer, so I'm cheating. But we have to get rid of VBS2 also. What's VBS2 equal?
Vx.
Okay, I agree. It's a version of Vx.
Negative.
Yes. So bulk's 0, 0 minus this source voltage. So 0 minus Vx. This is also minus Vx. So it was Vx, but just the direction. Yep. It matters which direction you go. Okay. Then there's a trick for Vx. Did anybody figure that one out?
You write V test in terms of Vx, and then solve for Vx.
There's a pretty straightforward way to find Vx. V test doesn't come into it.
Would it just be I test times R01?
Yes. So this I test, when it comes down here, it splits into the 3 branches here, but then it comes back together here. It recombines. And this is also I test. So Vx is just this I test times R01. And now you can say, okay, now I have an equation. Oh, 58, I'm not going to make it by time. I'm sorry. Minus I test times R01. And this one's also minus I test times R01. And now we can replace all 3 of these unwanted voltages with voltages and currents that only include I test and V test. So let's do that. I'm going to go over, but the video will have it. So I have my original equation. I have I test equals GM2 times your VGS2, but that's minus I test times RO. So I test times RO1. Better to use a dot maybe. And then you've got the second term. It's minus GMB times I test times RO1. So that takes care of these 2 terms. And then you have my pen stopped again. This is really annoying. Have V test over RO2. And then you have minus Vx over RO1. So you have minus I test RO1 all over RO2. And like I said, I'm going to keep going. If you have to leave it, it'll be at the end of the video. But it's just probably another minute and a half. Okay, so then you want to take all the I tests to one side. So this is I test. So I test times 1 is I test. And then when you move these over, the minus sign goes away. So you have GM plus GMB times I test RO1, I think, and the other I test plus RO1 over RO2. So I moved this term and this term and this term over to the other side. So all the I tests are on one side, and that just left this V test over RO2. Okay, one more step, 1 or 2 more steps here. Okay, up to there, good? Okay, what we actually want is V test over I test. So I'm going to divide both sides by I test to get rid of this, and then multiply both sides by RO2 to get rid of this RO2. So we get RO2 times 1 plus GM plus GMB. Oops. RO1 plus RO1 over RO2. Almost there. Whoops. Okay, and then let's do a couple of assumptions here. Let's do ROs are all about like 100K or something like that. And GM, let's say it's greater than 10 times GMB. So in other words, GM is much bigger than GMB. What's this equation become?
RO2 times RO1, or wait, 2 plus RO1 times RO2.
Okay, so I agree that that turns into a 1. But this right here, this is going to be much bigger than 1. This is going to be like 10K or 100K times 0.1. So it'll be 1,000 times bigger than this term or this term. Okay, what about GM and GMB? What's left there?
Just GM.
Yes, so what you end up with is GM times RO1 times RO2. Okay, and the whole goal of this story was, even though I'm 3 minutes over, so sorry again, is that when you had a single transistor, remember when you did the analysis, you got that it was RO? It looked like a resistor of size RO. This one looks like a resistor of size RO squared. You'd think if you stack 2 transistors, it would be resistors in series and you'd get 2 RO, but the ROs actually multiply and give you perceived resistance of like 1,000,000 just by putting 2 transistors on top of each other.
Doesn't the GM greatly bring it down though?
GM can be like somewhere between, see if my pen decides, oh, it works again. I don't know what's going on with this. Okay, it stopped working again. GM is often, not always, and the really small currents like on an IC, they get smaller, but for the breadboards that you have, somewhere like this is reasonable. So you're dividing this by 100, but you have 100K times 100K. So it's still gigantic. It's mega ohms. But yes, it does bring it down a little bit. Okay, sorry for the dash at the end.
So basically having 2 transistors instead of 1 allows greater gain in your amplifier? Because
Crazy
you have
greater gain, yes. Your gain gets multiplied by 100,000 or whatever, how much ever you've increased it by.
Got it.
Yeah, and I'll give you the moral of the story on Friday, just because this is so useful. Cascoded transistors are any place you need a big resistor, just stack a couple transistors and you've got gigantic resistance, or perceived as gigantic resistance. Okay. Any questions? I will post up the video. All right, bye-bye.
Bye, thank you.
All right, bye-bye.